aldol begins with an aldehyde or a ketone. Claisen needs to begin with an ester. Which is more acidic, aldehyde or ester? So an ester is a little bit tougher to deprotonate than an aldehyde is, but we can do it. Pluck an alpha hydrogen. Like that. And make an enolate. And I bet some of you, the 3 that are awake, say, but why would you do that instead of attack the carbonyl carbon? Is it possible for this to attack the carbonyl carbon? Uh-huh. It is possible. Yay, it's even likely. But if that OIT attacks the carbonyl carbon, you get this. A tetrahedral intermediate that's not stable. So you fold down and kick out your weakest base, your best leaving group. So you get back where you started. This process of attacking the carbonyl carbon and folding down and kicking out, it's an equilibrium thing, and that reaction is happening simultaneously, but it doesn't lead to fruitful product change stuff, so we're going to ignore it for the most part. But I will say that it's important when you're doing a Claisen that you choose a base that is identical to the leg on your ester. Why would you do that? Because when that base attacks the carbonyl carbon to make this green compound down here, this green tetrahedral intermediate, if you had used a different base, let's say you used a propyl instead, you would have a mixture of ethyl esters and propyl esters up here, as in you would have some propyl ester enolates and some ethyl ester enolates, and that's just disastrous. That crossed aldol, remember that disaster? Yeah, you don't want that. So make sure that the base you choose to use here is identical to the leg of your singly bonded ester. Okay, so pluck an alpha hydrogen because that enolate is going to lead to some useful product formation. Attacking the carbonyl does not, because we chose an identical leg. Okay. Claisen is very similar to aldol in that after you make an enolate, you attack the carbonyl carbon of another ester that's in solution. There's lots of ethyl ester in solution that has not turned into enolate. I wish this were a little more spread out, but we're going to make do. That green bond is my new bond. And this carbon is this carbon. So you should have an O minus, O ethyl leg, and a methyl carbon on that one. So this intermediate has 2 oxygens on it. We can fold down and kick out our weakest base, our best leaving group here. I'm going to swing that carbon around that direction so that you can more easily see what's happening here. And here's my product. Ish. What? Yeah, this is my product. Ish. Can NaOH pluck an alpha hydrogen from an ester? Yeah. Does it favor products at equilibrium to make all enolate in solution? No. But can NaOH pluck a hydrogen from betwixt 2 carbonyl carbons? Of course it can. So NaOH plucks an alpha hydrogen from between the 2 carbonyl things you just created to give you another enolate. This enolate. This enolate is super stable, remember, because it's got delocalization this direction and that direction. Super stable enolate. If you look at the reagent choices for the Claisen condensation, it has naoate and hoate added to an ester, and then follow up with H3O+. I'm going to say, let's follow up with H+ only, and I'll explain why I say that. And I want to identify that hydrogen in green specifically. This is a really weird color combo I've chosen here. I know. So that green hydrogen came from the acid workup step that came after naoate and hoate. The Claisen reaction, the Claisen condensation, must have 2 alpha hydrogens in order to work. Because if you don't have 2 alpha hydrogens, you won't get to this step. And because I have bad habits, I did not write all of these things, all of these reaction arrows, as equilibrium processes, but they are all equilibrium processes until you get here. This deprotonation, alpha deprotonation, to make this new enolate, this step is irreversible, because at the point where, if I make it all one color now, at the point where you've got this and naoate in solution, if we draw our equilibrium reaction stuff and we revisit the first video about enolates, we would see that a beta diketo type compound has a pKa around 10.7. And we would see that, this is supposed to be the enolate. Sorry, no wonder. A beta diketo compound has a pKa around 10.7, and ethanol has a pKa around 16. Equilibrium favors products and products only. That difference is big enough that we would say it's almost exclusively products. So that's why we say this step right here is irreversible, because the pKa says it's irreversible. The pKa says you have products only when those two are in solution together. They mandatory form this. Okay, what's the big deal? Claisen must have 2 alpha hydrogens in order to get appreciable amounts of product, because otherwise the reactants are favored. The ester form is favored until you get to this irreversible enolate, and then you do workup to protonate that enolate. Claisen must have 2 alpha hydrogens. Okay. The product of a Claisen is a beta keto ester. Beta keto ester. So here's the reaction we drew. There's the product we came up with, beta keto ester. Here are 3 more examples of Claisen. There's a part of me that says, let's do this together. And there's a part of me that says, nah, you got to try it. I'll walk through it a little bit. This top example, you're going to pluck an alpha hydrogen, make an enolate. Enolate attacks a second ester compound. And then you fold down and kick out your ester. That's real messy up there. You're welcome. Try it on your own, but you get that product. The next one is 2 esters in the same molecule. It's going to do an intramolecular condensation and make a ring thing. How big is that ring going to be? 6, like that. And in that last one, do we get this product? No, you don't get that product because there's not 2 alpha hydrogens. Students find this problematic sometimes because you can draw a very reasonable looking product of that bottom example, but the Claisen is a reversible reaction, and unless you have that last acid-base step to make it irreversible, you're going to get no condensation product overall. Claisen has to have base followed by acid in order to work. Claisen has to have 2 alpha hydrogens, mix the ester in with base, and then it's going to need acid as a workup step to make sure that you get a neutral product in the end. The Diekmann condensation reaction, we're going to draw these together. You should try it though. The Diekmann condensation always makes a ring. The Diekmann always does an intramolecular cyclization. Let's do it. I wrote out this top example so that we could go through it together, and then I thought, nah, we don't need to do that. You can do that. I've got faith in you. Well, let's talk about this bottom example because there's one little caveat, one little tricky thing in the bottom example. What's the tricky thing? Claisen must have 2 alpha hydrogens. So could this side become the enolate? Technically, yes, but would you get condensation product out of that? Claisen condensation product? No, because you've only got 1 alpha hydrogen. So knowing you have to have 2 alpha hydrogens, that's going to require that this side become the enolate. We can run through this mechanism quickly. That side becomes enolate. And we attack the carbonyl carbon on the other side. We get a 1, 2, 3, 4, 5, 6-membered ring. I'm not trying to match things up. I'm just sticking numbers on a 6-membered ring, and then I'm going to figure out where things go. On carbon number 1, I should have a carbonyl ester thing. Carbon number 1, carbonyl ester thing. Carbon number 5 needs a methyl. Carbon number 6, O ethyl and O minus. Claisen folds down and kicks out your ester leg to get you here. So many students think they are done at this point, and I say, no, not yet. The base plucks an alpha hydrogen. Which alpha hydrogen? The one from betwixt the 2 carbonyl carbons. Because that one is way more acidic than the alpha hydrogen over here, because it's between 2. And then you add acid workup to get you this final product, which is actually identical to this pink one over here. But Claisen does not work unless you've got 2 alpha hydrogens. This step is irreversible so that you can get some appreciable Claisen product. Yep. That's pretty much all we have to say about Claisen. So I want to say one thing to you before we move back to the PowerPoint slides. This is an acid that you had to learn the name of long ago when we learned naming carboxylic acids. This is malonic acid. If you turn this into an ester, naming esters, it's a malonate. It's a dimethyl malonate here. malonic acid, dimethylmalonate. What's cool about things like this? It can easily turn into an enolate because you have an alpha hydrogen betwixt two electron withdrawing groups. Let's see what we can do with malonate things. You really should predict that top Claisen on your own, that top Dieckmann. Dieckmann means Claisen making a ring. So here's that malonate that we discussed. This is not dimethylmalonate, this is diethylmalonate. What do you suppose happens to diethylmalonate when you add NaOH? Pluck an alpha hydrogen and make an enolate. And then you add this thing. This thing is an alkyl halide, a primary alkyl halide. And our flowchart says primary alkyl halide, SN2. This enolate attacks your carbon and pops off your Br, SN2, to give you this product. This bond right here is the new bond that was made by the enolate attacking SN2. Then what the heck is the next step? Hydroxide, water, heat. Hydroxide saponification. Saponify those esters. Chop, chop. Turn those esters into carboxylic acids. Hydrolysis in base. Saponification. Hydrolysis in base. Turn those esters into carboxylic acids, except because you're in base, they're carboxylates. So then the H3O plus protonate those carboxylates, and then the heat. What the heck does the heat do? This. That bond is not visible. It's totally visible on my slides. There's a bond still here. That's a single bond, not a double bond. That last step is decarboxylation. Do you need a reminder how that works? Let's do a quick refresher of how that works. So this was our product prior to decarboxylation. What does the mechanism of decarboxylation look like? In order to draw the mechanism, I'm going to spin around this carboxylic acid bit to point this direction. So that I can then draw some curved arrows. All in one fell swoop. We do that. You're going to lose CO2, so you need to make a new double bond between carbon and oxygen. So hydrogen's electrons donate to do that. That would explode that carbon. He would have too many electrons, so you give the other carbon, a neighboring carbon, a double bond. That would explode that carbon, so we're going to fold out electrons to attack that H simultaneously. We end up with a C double O, CO2. We end up with an alkene and an OH and an OH. And our tail, our little fish tail down here, stays in place. But wait, that's not the product you showed. You're right. This bit is an alkene and an alcohol on the very same carbon. It's an enol. It has to tautomerize. This is not a legit tautomerization mechanism, but I'm cool with it. So if we tautomerize that thing, we end up with CO2 and a carboxylic acid. Yep. The malonic ester synthesis starts with a dimalonate, diethyl, dimethyl, diisopropyl, whatever, a dimalonate compound, turns it into an enolate, does an SN2 reaction, and then gets rid of the esters and decarboxylates. That's the malonic ester synthesis. The malonic ester synthesis is an old style way to make an alpha substituted, I should make this an ester, to make an alpha substituted acetic acid. So we started with this guy, added this SN2 substrate. This is not a sequence of steps. Remember, it took multiple. But we ended up with a substituted acetic acid. We made a new bond between the alpha and the beta. The beta carbon was the carbon that got SN2'd upon. The alpha carbon is the carbon that was there all along. So if you were told, propose a synthesis of the following. If you recognize this is acetic acid, and I've got substitutions at the alpha carbon, yeah, you can make this thing through the malonic ester synthesis. What does it look like? Let's do it. I need to start with a dimalonate. We're going to choose diethyl. Why not? A dimalonate. I need to deprotonate it, pluck an alpha hydrogen, and I need to add a good SN2 substrate. I need to make alpha beta bonds. It does not matter which you make first, but you're going to need to make 2 alpha beta bonds. We'll make this one first, just 'cause. So this beta carbon is this carbon that got SN2'd upon. This carbon with the arrow, it's all the same. Yeah. I need to make another alpha beta bond. So lather, rinse, repeat. Pluck an alpha hydrogen. Add a good SN2 substrate. This time I need to add 4 carbons. 1, 2, 3, 4 with a leaving group at the end. Does it have to be a halogen? No. It could be another good leaving group like a tosyl, a mesyl, a tryptyl. Sure, there are other options. I get this guy. Four carbons get connected from my blue thing. 4 of them. Plus my pink thing. I just realized I left off a T. And this is my product, except I need to saponify, acidify, and decarboxylate. Saponify, acidify, decarboxylate. Saponify means hydrolysis in base. Is base the only way to hydrolyze? No. In fact, if you add acid, water, and heat, acid, water, and heat can take care of turning the esters into acids, and it will leave you protonated in the end. Oops, I left off a carbon. That's what I get for trying to talk and draw at the same time. If you do acid, water, heat, can you tell what that is? If you do acid, water, heat takes care of turning the esters into acids and leaving you a neutral product in the end of that. And because you're heating, you can decarboxylate all in one fell swoop. Swoop, swoop. There you go. Malonic ester synthesis. Way back in those beginning carboxylic acid nomenclature days, you had to know malonic acid. You also needed to know acetoacetic acid. This is acetoacetic acid. So if you make this acid end into an ester, it's acetoacetic ester. So this compound is ethyl acetoacetate. Ethyl acetoacetate. Mouthful, I know. The acetoacetic ester synthesis is so similar to the malonic ester synthesis. The first step is going to be pluck an alpha hydrogen. The next step, add a good SN2 substrate, SN2. And that heading down, saponify, but this time you're only going to turn your one ester into a carboxylate. This is a ketone and an ester. Do not make both sides a carboxylate. Then you acidify, and finally decarboxylate. If you pay attention to our decarboxylation mechanism that we drew previously, the decarboxylation mechanism gets rid of a carboxylic acid. It was not hard to choose what to get rid of in malonic acid because both of them were acids. But in acetoacetic, you're going to keep the ketone version and get rid of the carboxylic acid end. That CO2H leaves as a CO2. The product of the acetoacetic is a substituted acetone. So this is my acetone. We made a new alpha beta bond. The alpha was there from the acetoacetic in the beginning. The beta was brought in from your good SN2 substrate. Let's walk through this first synthesis together. Maybe you should try those others on your own. One thing I want to point out, we're going to make an alpha beta bond. So how many bonds need to be made in this one? One and only one. Malonic and acetoacetic both make alpha beta bonds. Uh-oh, this one has two alpha beta bonds. So this synthesis will require first sequence and then lather, rinse, repeat, and a second sequence of reactions. Malonic and acetoacetic make alpha beta bonds. We've got two alpha beta bonds here as well. So we're going to have to do a sequential thing with that bottom one. We're going to work on the circled one together. As I pointed out on the slides, we're wanting to make an alpha beta bond. So there's only one alpha beta bond to be made here. Are we going to do acetoacetic or malonic ester? Acetoacetic, because we have a substituted acetone. This is a ketone product, not a carboxylic acid product. So we can start with ethyl acetoacetate. Ugh. Pluck an alpha hydrogen. Add a good SN2 substrate. Because we know how many carbons we need, we're going to add that as our SN2 substrate. The new bond. I did not color code, but the new bond is this one. It's the super thick one. It is not a double bond. It's just a super thick bond so that you can see which bond was the new one made. And I can then saponify, acidify, decarboxylate, or I can recognize that hydrolysis in acid is also a thing. So I can hydrolyze in acid. That will make sure that I get a carboxylic acid and not a carboxylate. And if I heat it at the same time, I get my product all in one step. It's drawn in a little different orientation, but it's my product, I promise. So malonic and acetoacetic are frequently referred to by name, but there are lots of varieties of things like this, such as this one. When you add this aldehyde and this diethyl malonate together with naoate, it's going to do an aldol-like condensation. Give you that product. I have faith that you can understand how that works, but maybe you should try drawing it. Any idea what hydroxide and water and heat might do? Saponify, leave you with carboxylates. Acidify, decarboxylate. How about another condensation reaction that does not have a name? Sodium hydride, what's it going to do? Pluck an alpha hydrogen. That enolate attacks the carbonyl carbon. This is an acid chloride. Remember, that's way up there on the reactivity scale. So I'm going to have a tetrahedral intermediate after those arrows I just drew. Tetrahedral intermediate, fold down, kick out your weakest base, your best leaving group, and that happens to be chloride in this one. Here's my product. So all of those condensation reactions we just walked through, they're great, but they're a little bit old news, a little bit old school. Those condensation reactions are very wasteful, as in they're not very atom economical. It's a thing, you should look it up, even though we've not talked about it much. Atom economy means how many of the atoms in your reactant that you begin with end up in the product that you end with. When you start with diethyl malonate, in the end, the product that you make has 2 carbons from diethyl malonate and 1 oxygen from diethyl malonate. Otherwise, all those other atoms are completely wasted. Becoming more economical has become a recent focus, a recent goal of chemists. And so all of those old style condensation reactions are not very atom economical. So organic chemists looked for a new way to do similar reactions, but in a more atom economical fashion. In comes LDA. We've already seen LDA previously. LDA is a super strong base. That's lithium diisopropyl amide. LDA, super strong base. What's it used for? It can quantitatively pluck an alpha hydrogen and turn all of your starting ketone, in this case, into enolate. Done. There's our enolate, all enolate. Was the diethyl malonate and ethyl acetoacetate a quantitative deprotonation? Yes, but it's because we chose and had to choose a beta diketo compound. We had to manipulate the variables to choose a substrate that has a very acidic hydrogen. But there's nothing special about this substrate. It does not have very acidic hydrogens. It's got pretty high 25 pKa hydrogens. But LDA will absolutely quantitatively deprotonate it to become enolate. And then you can add tons of things next. But if we add this good SN2 substrate, we get that final product, where we made a brand spanking new alpha beta bond, just like we made alpha beta bonds in the acetoacetic and malonic ester synthesis. But this time we don't have to saponify, acidify, decarboxylate. We don't have to throw away so many of the atoms that we started with. We get to keep all of the atoms that we started with. So maybe you notice this synthesis is much shorter, but it's also more efficient, more atom economical. LDA is very useful and flexible for being able to alkylate many types of alpha carbons. So let us work on a synthesis problem. How would you prepare the following by alkylation of a ketone? Let's draw it. So just like all the others, alkylation with LDA makes alpha beta bonds. So I could propose a synthesis to make this alpha beta bond. We're going to draw it in blue. That would mean this enolate attacking something like this good SN2 substrate. Does it have to be a halogen? No, but sure. So this is if I make that blue alpha beta bond. This is if I try to make the green alpha beta bond. This is if I try to make the pink alpha beta bond. Pink, green, and blue. You guessed it, you're going to have to vote. Is there a method that you think is more appealing than another based on what you know at this point? Pink, green, or blue? Blue, green, or pink? We are going to walk through this process. But before we do, we're going to take a detour to talk about kinetic and thermodynamic enolates because it applies. Don't let me forget to come back and talk about this. If I have this ketone, I have two different types of alpha hydrogens. Alpha here, alpha there. Two different types of alpha hydrogens. If I pluck off a left alpha hydrogen, I can make this enolate. That's the oxyanion version. Here's the carbanion version. If I pluck off this armpit hydrogen, haven't you missed talking about armpits? I can make this enolate. That's the oxyanion version. This is the carbanion version. One of these enolates is considered the kinetic enolate, and one is considered the thermodynamic enolate. Oh, brother, this again? Unfortunately. Do you remember when we talked about kinetic and thermodynamic stuff, and we talked about 1,2, 1,4 addition stuff? We looked at the alkene to figure out the stability. This is a tri-substituted alkene. The oxyanion is a tri-substituted alkene. This oxyanion is a tetra-substituted alkene. Which alkene is more stable? Tetra. So which alkene, which enolate is the thermo? This one. This is the thermodynamic enolate. This is the kinetic enolate. Thermodynamic enolate is the more stable alkene. Kinetic enolate is the less stable alkene. Thermodynamic enolate comes from the alpha hydrogen on the carbon that has the fewest alpha hydrogens. The kinetic enolate comes from these very accessible, quickly accessible, very available, multiple alpha hydrogens side. Thermo comes from the alpha with the fewest hydrogens. Kinetic comes from the alpha with the most hydrogens. So what are the exact conditions to get the thermodynamic enolate to form or the kinetic enolate to form? Well, LDA is really great at forming enolates. It's really great at it. If you want the thermodynamic, you want to be at a warm temperature. What? 0 degrees? Warm temperature? Are you crazy? Well, 0 degrees. LDA is normally present at -78. That's the cold temperature. Believe it or not, 0 degrees is the warm temperature. LDA is a quite bulky thing, so it's pretty difficult for this kind of base to go into that little baby armpit and pluck that hydrogen. It is capable, but it's not great at it. More commonly, to get the thermodynamic enolate, you use a smaller base. An NH2 minus base has the same type strength that LDA does, similar pKa, but it's not as bulky, so that's often used. If you're using a smaller one, sometimes you will maybe specify 0 degrees, but it's not always specified, unfortunately. Sometimes you just have to assume it should be thermodynamic because of the crowding steric stuff. Sodium hydride is an okay base for that sometimes because it's small. LDA is our favorite. LDA at -78 is our favorite for the kinetic enolate. Okay, believe it or not, I remembered. We got this stuff to talk about. Blue, green, or pink? Well, if we go back to considering the ketones that these things come from, that blue enolate would come from a ketone that's not symmetric. So you could potentially control taking this alpha hydrogen rather than that alpha hydrogen using kinetics and thermodynamics like we just discussed. There's more information. Hold on. For the green enolate, the ketone, not this enolate, but the ketone version, there would be 2 alpha hydrogens here and 2 alpha hydrogens there. One is not particularly more crowded than another. One is not more acidic than the other, really. So the green is the worst choice because you can't really control this with kinetics and thermodynamics. When you use the green ketone, this green ketone, sometimes you might get this guy to be the enolate, or sometimes this one might be the enolate. So the green is the worst choice. The pink one, there would be 2 alpha hydrogens here and 2 alpha hydrogens there. One is not more acidic than the other, but the pink actually has an advantage that the blue does not. The pink is a symmetric ketone. So you really don't even have to worry about kinetics and thermodynamics and picking a bulky base or a small base or a high temperature or a low temperature or all those other variables. If you pick the pink, you can just slap LDA on there without specifying temperature and you don't have to worry about it. Well, let me show you what I mean. Blue could be a usable thing. We would have to mandatory specify LDA at -78 because absolutely we need the kinetic enolate. And so this 3 hydrogens versus this 1 hydrogen, you gotta have the kinetic enolate. And then we could add this methyl bromide. Blue's doable, but not my favorite. Pink is actually my favorite because you can start with this ketone that is symmetric and you add LDA, ain't no worries about no temperature. Then you add butyl bromide. Done. Blue is usable. Pink, in my opinion, is best. Green is the worst. So LDA is often a great synthesis choice, often a more flexible synthesis choice than the malonic ester, acetoacetic ester stuff. Because malonic and acetoacetic, you only make substituted acetones and acetones and acetic acids. But LDA, you can do so many things. The possibilities are endless, almost. If we move on to the next slide that says enamines, oh boy, I thought we was already tested on those. Enamines are synthetic equivalents of enolates. You say, what? Yeah. Aldehyde or ketone plus a secondary amine put those things together, you make an enamine. It goes through this iminium intermediate, but that's not good enough. That's not the final product. You go through to dehydrate, go through to eliminate, to make this enamine product. This was an iminium, not final product. Go through an elimination to make an enamine. The slide says enamines are synthetic equivalents of enolates. What does that even mean? It means that if I now add a good SN2 substrate, I can get that thing added to my alpha carbon. Yeah, really. Nitrogen folds down and kicks out to attack that carbon with your Br. You get nitrogen, doubly bonded. Positive charge, and you add 3 carbons, 1, 2, 3 carbons, 1, 2, 3 carbons to your alpha position. And then you can do hydrolysis. What? Why would you do that? You just put it on. Well, enamines are especially good for obtaining the thermodynamic enolate. Huh? Yeah. Remember back here, we said LDA, it's not super stable at 0 Celsius. It really prefers to be at -78. So we said we could maybe substitute a base like NH2 minus. It's not super great either at this. Sodium hydride is maybe sometimes used, but really the thermodynamic enolate is the favored option when you use an enamine. Let's see. If I were using that very ketone that I just showed, when you add a secondary amine, doesn't matter what that secondary amine is, we're just making it up over here, a secondary amine to that thing, at your iminium step, whoops, that's a nitrogen, at your iminium step, some base is going to take a hydrogen. Is that base going to take a hydrogen from the armpit or from over here? Enamines favor Zaitsev elimination. So that base takes a hydrogen from here, making this enamine. This enamine is equivalent to this thermodynamic enolate that we saw earlier. This is oxygen with a lone pair. This is nitrogen with a lone pair. This enolate can be drawn as the oxyanion version, the way I just did, or it can be drawn as the carbanion version. This enamine can be drawn as this enamine, or you can draw the resonance version where it's iminium looking. It's squeezing over here in the corner. Iminium, carbon with a minus, nitrogen with a plus, an iminium version. So this is the carbanion version. This is the carbanion-ish version of an enamine. So that can attack SN2 substrates. Enamines are synthetic equivalents of enolates. If you want the thermodynamic enolate, an enamine is a good way to go. Whew, I'm tired of talking, and I know y'all are tired of watching. Hope you enjoyed it.